So far as you can see, our mass spring system lies on the horizontal frictionless floor, right? But now what happens if we just hang the spring and the mass, to the ceiling here? So it means that our mass spring system is just lie, along the vertical axis already. So does the period of the oscillations depend on the gravity or not? As you remember, when we talk about the horizontal spring mass system, the angular frequency is just equal to the square root of the k over the m, right? It doesn't depend on the gravity. But then, how about this structure? So the angular frequency will depend on the gravity or not. So let's explore this in these topics. So initially, okay, let's see that if we have the massless spring, right? If we have the massless spring, and let me just write down the massless spring, okay, and then with the spring constant equal to the k. So then the original length of the spring here, let's say that it just equal to the L naught. Oops. Okay, the original length of the spring is just equal to the L naught here. But now if we put a block of the mass m to the bottom end of the spring, right? So you can see that if we just move, if we just hold the block m, and the block m will just gonna go down, and then it's gonna stop at the new equilibrium position of the spring. Okay, so let's say that this one is the new equilibrium position of the spring when we have the mass m hanged with the spring. So it means that the spring will extend. The spring will just extend from its original equilibrium position by the distance equal to delta L. So let's say that delta L here. And then moreover, if we just write down the free body diagram of the block M, right, you can see that we have the mg is just going down, and then we must have the returning force of the spring going up, right? So the returning force of the spring here must be equal to the k, and equal to the k and then times delta L, right? It just comes from the kx, but now this x is extension equal to delta L here. So that's why we have the k times delta L as the returning force of the spring. Now in this case, we can get that the mg must be equal to the k and then times delta L, right? Because the spring is, the block is at rest, so the force must be equal to the 0. So that's why we can get something like this. Now, if we consider the motions of the mass, okay, if we consider the motion of the mass, so then this mass, right, it is gonna oscillate up and down about this new equilibrium position of the spring. Okay, so let's say that the mass will have the expression equal to the A. Okay, so let's say that the mass will have the expression equal to the A into this direction, okay, to be positive. And now for the Y, right, for the Y, this is going to be the extensions or the compression of the spring from the new equilibrium position. So let's say that it just equal to the Y. Okay, so the Y here is going to be the extensions of the compressions of the spring from the new equilibrium position here, right? So it means that we just make this one to be equal to 0, right? Okay, so if this length equal to the Y, it means that this length, okay, this length must be equal to, okay, the whole thing here is equal to delta L, but this one is equal to the y already, so this one must be equal to the delta L and then minus the y. So we just do the same thing, we just draw the free body diagram of the block, right? So we have the MG here as usual, okay, and then we have the resulting force, right? So it's equal to the K and then times delta L minus the Y in this case. Okay, because net force in this case is not equal to 0 because we have the expression, right? Net force is not equal to 0. Then you can see that, okay, from the net force equal to the mass m and then times the expression. Okay, so again, let me just make the going up to be the positive and going down here to be the negative, right? Then we can get our net force, right, equal to the K and then times delta L minus the Y, and then minus the mg, because this is going up and this is in the downward direction, so that's why this must be positive and this must be negative, and then equal to the m and then times the a. So now let's just push the k into this parenthesis, right? We have the k times delta L minus the ky minus the mg and then equal to the m and then times the a. But now you can see that the mg is equal to the k times delta L, right? So it seems that we have the k delta L here and we have the mg here, okay? So it means that the k delta L minus the mg must be equal to the 0. And then finally we have that the expression equal to the negative k over the m and then times the y, right? Which is in the form of what? In the form of the fundamental equations for the simple harmonic motion, right? If you remember, we talked about this one already here. No, wait, here, right? It's called the fundamental equation for the simple harmonic motion. So I said that if any motion has equation of the motion in this form, right? So it means that that particle will move as the simple harmonic motion. And then these variables in front of the x, right? It must be equal to the omega square, okay? The angular frequency square. So if we compare to this one, we just have the same form, okay? So it means that the block M here, right, will move as the simple harmonic motions, and then you can see that this term, okay, this term, oops, okay, this term is gonna be equal to, oops, is gonna be equal to the omega square, okay? Or we can get that the omega equal to the square root the k over the m, which is the same form as the horizontal spring mass system, okay? So what can we conclude from this one, right? We can conclude that the omega, right, is independent from the gravity g, and that's it, okay? The omega is dependent from the gravity g. On the other hand, we can say that, okay, if we just do this experiment, right, on the earth, okay, and if we go to the moon and we just do the same experiment, we should get the same omega, right? We should get the same angular frequency of, the block equal to the square root k over m, because in this case the omega doesn't depend on the gravity of the planet.